Hello, my amazing students. This is Mrs. A, and I just want you to know the depth of my dedication to you. I am sitting in a walk-in closet at our little vacation home, and I am going to teach you 7.2 from this little closet. So if this echoes just a little bit, it's because I'm sitting in a walk-in closet, and the walk-in closet's pretty empty because, like I say, this is a vacation home, and we're having a blast, and I just had a great dinner of lasagna and broccoli and garlic bread, and we're having a ball, but I'm going to get your 7.2 finished right now. But before I start 7.2, I want to recap one really cool thing that I talked to you about in class that's in your PowerPoint. If you're ever asked to find the confidence interval for a proportion, but you are not asked to give anything else, you can use this really cool function on your calculator. Okay, so to get to this function, all you have to do is put in the stat and go to test. And then you're going to choose the 1 prop z integer, or interval, not integer, interval. So that's the interval for the proportion. And then all you have to put in is the x, which is your number of successes, your n, which is your total number of sample size, and then you're going to put your level of confidence, 95% or whatever it is on your problem. You're going to hit calculate, and it's going to give you the interval back. It's also going to give you your p-hat, which notice you did not have to put your p-hat in, but it's going to give you your p-hat out. So that's really, really cool. So now we're going to start 7.2. Okay, so in 7.2, we're talking about estimating a population mean, whereas in 7.1, we were talking about estimating a population proportion. So remember, I told you the steps that are going to be the same in each one of these when I showed you that little piece of paper. So here you're going to see that it is the same, but just a little bit different because we're looking for a different thing. The main goal of this section is to present methods for using a sample mean, x bar, to make an inference about the value of the corresponding population mean mu. So we've got an x bar, we're looking for the mu. Right, so there are three main concepts. Does this look familiar? Remember, we had the same three concepts in 7.1. Finding a point estimate, and the x bar is going to be the best point estimate for the mu. And the confidence interval, we're going to do the confidence interval. It's got the same idea. We're going to go about it just a little bit differently because, again, we're looking for a mean and not a proportion. And then how to find the necessary sample size for the population mean, to be able to estimate the population mean. So now a point estimate is a single value estimate for a population parameter. The most unbiased point estimate for the population mean is the sample mean, x bar. So now here we have a bunch of data. So what do we do when we have a bunch of data? They haven't given us an x bar, but can't we use all this data to stick it in our calculator to find the x bar? So that's the first thing they're going to do, is they're looking for the point estimate for the population mean, which is the x bar. So we enter all of these into the calculator, and remember how you do that is going to stat edit, and then you're going to put them all in the list. Okay, so when you do that, you end up getting the sum of each one of those x's divided by the n, which was 40, and you get 130.8. You could have added them all up, or you could have stuck them in there. Doesn't matter. Your point estimate for the mean number of friends for all users on the website is 130.8 friends. So we have our x bar. And now what we're going to do for the rest of this thing is look for our true population mean. All right, so now confidence interval for estimating a population mean, where the sigma is not known. Now, do you remember that the equation for finding the population mean involves knowing the true mean. So very, very rarely are you going to have access to the true standard deviation of the population. So this one that we're doing right now is going to be the one you're going to use most often because you do not have the true standard deviation. How could you? You don't have the true mean. So how could you have the true standard deviation unless it was handed to you? And very often it is not handed to you. So we're going to use the first method here is going to be the one that you're going to do most often. Okay, now remember at the beginning of this tape on the 7.1 portion, I gave you this little cheat sheet. These were the big 3 points here. Confidence interval involves each one of these steps. And the third step here is verify requirements. So let's talk about the requirements for the estimation of the mean. Okay, so here we are. Confidence interval for estimating. Here are the requirements. All possible samples of a given size have an equal probability of being chosen. That is, a simple random sample is used. Okay, either or both of these conditions are satisfied. The population is normally distributed, or n is greater than 30. Either one of those being solved is going to allow you to use this method. Okay, so we have our level of confidence. We talked about that in 7.1. Okay, and we have the same type of thing going on here. The confidence interval, the confidence level, is the part that's under a two-tailed curve. It's the part that's in the middle. So then remember, 1 minus the confidence level is the alpha, and so the alpha must be split into the two tails. So that's where we get the alpha over 2 and the alpha over 2. And then the critical value is the part that has the alpha over 2 to the right. So this would be the critical value. All right, so here's the 1/2, 1 minus c, alpha, 1/2 alpha. And on the other side, we have the 1/2 alpha. So if the level of confidence is 90%, that means that we are 90% confident that the interval contains the population mean. So here we have 90% in here, which means we have 10% residing out here in the tails, which means half of the 10% and half of the 10% would have to be in each tail. So that's why that's 5%, and that's 5%. And then we would have to go to our table and find the z-score for the 5% to get the critical value that goes with it. Okay, so when we look at our table, we get 1.645, or remember down here on the right-hand side, the bottom of your table, you have common critical values, and there's the 90, and there's the 1.645. So there's your whole table, but you have this little cheat sheet down at the bottom right-hand corner. All right, so now we're going to talk about a new distribution. We're going to talk about a T-distribution, and we use the T-distribution when our sigma is not known. The student's T-distribution must be used instead of the standard normal distribution when sigma is not known. Your standard deviation of your population is not known, and so we have to use a different distribution. Okay, so this is the one we're going to use the most often because normally our standard deviation of the population is not known. So here we have to identify, just like we did before on our little sheet here. Okay, the very first thing was identify sample statistics, get your point estimate, verify your requirements, get your critical value, margin of error, confidence interval, and round your results. So we're doing the same thing here, going through the same process, a little bit different because we don't have a standard deviation, therefore we use a T-distribution. Okay, so first, identify our sample statistics, our N, our X bar, and our sample standard deviation. Okay, verify the requirements. Verify the requirements that we have a simple random sample and that the population is normally distributed, or and is greater than 30. Those are still the requirements, even though we don't have a standard deviation known. We are going to still be able to use the T-distribution because we are normally distributed. We're going to do a lot about the T-distribution in just a minute, so you know what we're talking about. There's my X bar, which is, we've already found that once, and then there's my sample standard deviation and the formula for that. Remember, the true standard deviation has, instead of the X bar, it has the mu there, and we don't have the information to get the true standard deviation right now. Okay, so then we have to identify the degrees of freedom. The T-distribution uses degrees of freedom, the level of confidence and the critical value, to be able to look up the critical value in the chart. Okay, so we need to know the level of confidence, and then we can find that T value, or the T critical value, that's going to do the same thing that we did when we had the Z table. Separates an area of alpha over 2 in the right tail of the T-distribution. And then C is the confidence level, and 1 minus alpha is C. And then, let me get this one there. There's our degree of freedom, as always, the number in the sample minus 1. And then confidence level is equal to 1 minus the alpha. For a 95% confidence level, the alpha is 5. So then we're going to, last thing on this slide, find the margin of error. And these are two formulas for your margin of error. And remember, I told you there were 6 cheat sheets on this whole thing. 2 for the proportions, 2 for the T distribution, and 2 for the Z distribution, and this is one of those cheat sheets there. Okay, so these you won't find in your textbook, because these I got out of another textbook, and then I've kind of mushed other things in there so that you kind of have one place to go for all of your important formulas. Okay, so then we're going to go to the next screen, and it says find the left and the right endpoints to form the confidence level. Yeah, I hope that looks familiar to you, except instead of the p hat, we've got the x bar, because we're looking for the mu. And then with an original set of data values, round the confidence interval limits to 1 more, and this is your rounding rules. Okay, so let's see how we use the student T distribution. Okay, so the big deal about the student T distribution is when to use it. We use the student T distribution when we do not know the population standard deviation, and when we do not have the qualifications existing to use the Z-score. So rarely do we actually know the population standard deviation. As a result, 2 facts are crucial: the distribution of the population and the size of the sample. If the population is not normally distributed and the sample size is small, then advanced statistical techniques that are beyond the scope of this book are required to estimate the population mean. So therefore, if we do not have the population normally distributed and the sample size is greater than or equal to 30, we cannot use the standard normal. Okay, we can't even use the T distribution if we don't have that. So let's stick to what we actually do use in this book, which is either the T or the Z. They're just talking about sometimes you have to go to more extreme methods that we don't cover in this elementary statistics class. Okay, but the T distribution is very easy to use. It's just, the trick is knowing when to use it and when to use the Z-score. And that's what hopefully you will be clear on by the time we finish this slide. Okay, so basically it says if either the population is normally distributed or the sample size is sufficiently large, then another distribution called the student T distribution may be used to calculate the margin of error for a population mean when the population standard deviation is unknown. So there's their justification for using the student T. We can use the student t-distribution when we don't know the standard deviation, but we do have a curve that's approximately normally distributed, and we have we have a size of our sample greater than 30. Okay, so here is the formula for the student t-distribution, and we have degrees of freedom in the student t. That's something that's different. Now, I don't expect you to know all of the ins and outs. I expect you to be able to use the student t-distribution. I don't expect you to understand everything that's going on with it. The big thing that I want you to understand is the big points. The degrees of freedom is the number in the sample, take away 1. Okay, to find a critical value, we're going to use the table most often, or we can use the technology, which we'll show you. Okay, the table is going to be used most often with the t-square, and I'll show you how to do that. Okay, now what we want to understand is that as the sample size gets bigger and bigger, the t-distribution begins to look more and more like the standard normal distribution. Okay, so basically they're showing you different cases where n is 3 and n is 12, and the curve changes a little bit, but it becomes more normal the larger sample size we have. Okay, now these are some key points that we do need to know. The student t-distribution has the same general symmetric bell shape as the standard normal distribution, which you just saw. It has more variability with wider distributions, and we expect with small samples. The student t-distribution has a mean of t equal to 0, just as the standard normal distribution has a mean of z equals 0. And the standard deviation of the student t-distribution varies with the sample size, but it is greater than 1, okay, which, remember, your standard normal is just 1. As the sample size n gets larger, the student t-distribution gets closer to the standard normal distribution. Okay, so properties of the t-distribution. The t-distribution is bell-shaped and symmetric about the mean. Okay, it has degrees of freedom n minus 1. Total area under the curve is still 1, or 100%. The mean, median, and the mode are equal to 0, just like the standard normal. Okay, and then it gets more normal as the sample size gets bigger. And they're showing you that it's coming down and looking more normal as your degree of freedom improves, gets bigger. So now, how do we use this thing? Find the critical value t of c. T sub c is the same thing as t sub alpha over 2 for a 95% confidence level when the sample size is 15. So if the sample size is 15, remember our degree of freedom is going to be 15, take away 1. So degree of freedom is 14. Now let's see if we can get a little bit closer to that table. Now notice that we have a level of confidence given, and once we know the level of confidence, we can follow straight down to our degrees of freedom here. Okay, so since we have a level of confidence of 95, we're going to follow down the 95 and come straight across to the 14, 2.145. Yes, it is as easy as that. Okay, so using the t-distribution is very, very simple to do. So now, when we look at this one, it says that, hold on, let me go back. It started doing an autoplay there. All right, so on this one, 95 degree means that 95 confidence level means that we have 95% of the area, or 0.95 under here, which means that we have only 5% to split here and here, which means we have 0.025 in this tail. Okay, so 0.025 is going to be going to the t sub c of 2.145, just like we looked at on the chart. Okay, in general, the value of t such that an area of alpha is to the right of t is denoted by t sub alpha. So remember, we're usually looking for an alpha over 2 in our purposes, but they're saying, what if you had everything in one tail? Then you'd have alpha in one tail and your critical area. So this is just a student T slide. We'll be using a lot of this as we go into hypothesis testing. Right now, all we're doing is alpha over 2 instead of alpha. Okay, so find the value of t sub 0.025. Now, that means we have that much to the right, which means we have 975 to the left. So we're going to look in our sorry about that. The whole family was paging me and I was getting a little distracted. But here's your student T, and we're going to do 0.025 to the right. So now what we're looking at is T 0.025 with 25 degrees of freedom, which means the sample size must be 26 because they're giving us the degrees of freedom. So now what we're going to do, over here to our area in one tail, which is here 0.025, and that's the one they gave us. And then we're going down to my finger is at 25 right there. So we're going to go to the correct column, which was straight across to here, and we get 2.060 is the critical value that goes with the area of 0.025 in one tail. There we have it right there. And the T-chart is just that easy to use. Okay, so here they're showing it to us again. They're showing going across from the 25 and then down to the 0.025. Because the 0.025 was in one tail, then we don't, and everything lines up. Because remember, if 0.025 was in one tail, that means that 0.05 would be in two tails. And it would also mean that you're talking about a 95% confidence level. So in the T-chart, it's all tied up together into one. Right, so now this one is talking about your book example. You're trying to find the critical value of alpha over 2, T of alpha over 2. Find the critical value corresponding to a 95% confidence level, given that the sample has a size of 15. Okay, so we're going to go to our chart here. Since our sample is 15, then our degrees of freedom is 14. We're talking about a 95%, which means that in the tails, we only have 5 together, which means we only have 0.025 here and 0.025 there, which means we're going to look down the same column we just looked down, but we're only going to go to 14. So in the last one, we went over here to my T-chart, and there's my 0.025. So we're still looking down that level, but now we're only going down to 14, which is right here, going across 2.145, and if you look over here, 2.145. There it is again. Okay, so if you're going to use technology to do this, then we're going to use a Tdistribution technology, which we will show you here shortly. All right, so if I'm going to do the same thing with this one, I'm going to use the calculator for this one. I'm going to use an inverse T, and I'm going to put in the degrees of freedom as 14, and on the inverse T, I use the area to the left of the T-score. What I'm going to do is I'm going to use this one, and it's going to give me back a negative T-score because I'm to the left. But I really, if I wanted this one, then I would just throw it positive. Your T-score chart is always going to end up giving you out a positive T, but here my calculator gives me a negative one. So I did inverse t, 0.025, because that's the area to the left right here, okay? And so then I put in my 14 degrees of freedom, and it gives me negative 2.144. Oops, that's really blurry. How do I get that? There, negative 2.1447, which becomes negative 2.145, which I want this one over here, so I say positive 2.145. So that's how you use the technology to do that. Okay, so now I just have a whole bunch of examples in here, which I'm going to let you do on your own. I'm not going to go through each one of these, but hopefully I gave you enough examples that you can see how to use the t distribution here. So lots and lots and lots of examples of how to use your t distribution. So then when we're trying to find the area in two tails, you're going to use the two-tail column. Here's some more examples. Like I said, I just loaded this thing up, area in two tails. Just follow through all these examples. The t distribution is so easy to learn, but I just wanted to make sure you had a very thorough understanding. Remember, your PowerPoints are posted, and you can just go through these very succinctly and make sure you know how to use your t chart very well. Finding the value of the area between negative t and t. That would be your confidence level, wouldn't it? So find the critical value for a confidence interval. Okay, so all of this is the same stuff. So I'm not going to go over all of this. I just gave you all the slides so that you could go through it. So now, here, we're going to start back here. Okay, so now we're starting to talk about something new. Finding the margin of error and of a critical interval for a population mean. So now we're starting margin of error. Everything before that was how to use the t distribution, and so I just gave you a whole bunches of examples, and I want you to go back through and do it until you are a master at the t distribution. So now let's start here with finding the margin of error of a confidence interval for a population mean. And again, remember, we're doing the ones with the sigma unknown. The sigma unknown means we're going to use our t distribution. So we have dental researchers want to estimate the mean leakage measured in nanometers of a new filling material for cavities using a simple random sample of 10 trials. Assuming that the population distribution is approximately normal and the population standard deviation is unknown, find the margin of error for a 95% confidence interval for the population mean, given that the sample standard deviation is 15.5. So here, this is key. We know the sample standard deviation, but not the true standard deviation of the population, okay? So we're going to remember the trials is 10. That means n is 10. That means n is less than 30. But we do have approximately normally distributed. So we can use the t distribution. So we go over here to the next one, and then we're saying, okay, we have 95%, which means we're going to have 95%. Our alpha is 1 minus 0.95, okay, and that's 0.05. So we're going to split that between the two tails. So our alpha over 2 is 0.025. So we've already done this once. We're going to look up the t that goes with 0.025. And since we have a 10 for our n, we're looking up degrees of freedom is 9. So it will not be the same answer that we got last time, because now our degree of freedom is 9. So we will do this one using the inverse t to get this one. Okay, so right here I did this one. I've got the degree of freedom is 9, negative 2.26. Okay, now remember that it's giving me a negative 2.26, but I'm going to go ahead, and they wanted the 0.025 to the right, And so I'm going to take the positive 2.26. Here you can see the positive 2.26. Now remember, we're not just trying to find the critical value, we're trying to find the margin of error. And so here we found the critical value. So now let's go further down to find our, now they're using the table to find the 2.26. We just did ours using the inverse t. Get the same answer both ways, but now we're going to have to go do the rest of it. So they did the inverse t also down here. This is on the next slide. So they did it both ways with the table and the inverse t. And there's the inverse t, which I just did on my calculator because I didn't know they were going to do it. And here is our margin of error formula. So now we're going to use that critical t right there, 2.262. They gave us our sample standard deviation of 15.5. We have our n is 10, so square root of n goes on the bottom. And we calculate that all out, and we get 11.08, which is our error. So now we can make our confidence interval. But this slide was just finding the margin of error. So we haven't gotten all the way to the confidence interval. We'll do that shortly. All right, so here we have the next one, example 816, constructing a confidence interval for a population mean. So a marketing company wants to know the mean price of new vehicles sold in and up and coming area of town. Marketing strategists collected data over the past 2 years from all of the dealerships in the new area of town. From previous studies about new car sales, they believe that the population distribution looks somewhat like the following graph. Okay, so this one right here, you know, it's got a bigger tail over here, doesn't it? So here is the graph, and the simple random sample of 756 cars has a mean of 27,400 with a standard deviation of 1,300. Remember, this is sample data. So we need to construct a 95% confidence interval using, we do not know the standard deviation of the population. We only know a sample standard deviation. So we're going to use our t-distribution, okay, and we're going to find the point estimate, which is going to be the mean of the sample right there. So they're just writing that down. And then we're going to find the margin of error, which we are going to use the same equation we just did, and that is right there. Okay, so we have to use our critical value, and our critical value was done on the slide before here. So 0.025, because we wanted a 95% confidence interval. And when we looked it up, since we have degree of freedom of 750, we get 1.963. Okay, you should be able to verify that on your standard normal, on your t-distribution table. And so then we go to our inverse normal, and we could find the same thing, but we would use positive 1.96, okay, because our t is going to give us back a positive. And then we put in our sample standard deviation and our size of our population, and we get 92.8. So that's our error. 92.8 is our error. But remember, the mean was in the thousands, okay? So subtract a margin of error from and add the margin of error to the point estimate. So here we go. We had the sample mean minus the error, margin of error, and then the sample mean plus the margin of error, and that gives us our confidence interval just the same as we did with our population interval in 7.1. Okay, so from 27,307 and 27,493, we have a 95% confidence interval. Okay, so there's another way to write it. And with 95% confidence, we can say that the mean price of new cars sold in the area is between 27,307 and 27,493. Okay, so now we have constructing a confidence interval. Again, this is just another example. Here they have 20, so our degree of freedom will be 19. We have a sample mean. We have a standard deviation of the sample. We do not have the true population standard deviation, so we will use T again. And here's just another example. And here they're showing you the TI 8384 using the T distribution. Okay, and there they go. Okay, so they got the standard, they did it to the back, to the front, made their interval, and interpreted it. You know, I always put way too many examples on these, but I would rather have you skip through examples because you're bored with them than not have enough examples to understand the material. So now what they're doing here on this slide, still example 8.17, they're trying to show you how to use the T interval, which is not under distributions, but remember when we did the proportions, we had PROPZINT function. This one is the same type of thing, but it is under stat, choose test. The T interval will go straight to the confidence interval without jumping through any of the hoops. And so you're going to put in your sample mean. And this sample mean right here, I don't know why it's an E. It should be an X bar. Okay, the sample standard deviation, that's correct. The sample size and the level of confidence. So you have to put all those things in, and then you press enter, and you get the answer of the T interval, and it goes straight to the confidence interval. So anytime you need to go straight to the confidence interval and you don't need to know margin of error, all that other stuff, you don't even have to find the critical value. Notice you don't have to find the critical value at all. You just enter that data and you go straight to the T interval. So that is pretty cool. Nice little shortcut when you are not instructed to show all of the individual steps there. So hopefully you will find that helpful. All right, so on this one, you randomly select 16 coffee shops. Now notice, the T distribution has to be used because our N is less than 30 and our sigma is unknown. Okay, so, but the temperatures are approximately normally distributed. If that wasn't the case, we wouldn't even be able to use the T distribution. So they're going through another example here and using the chart, and they're showing you how they're using it. They're finding out their margin of error, left point, right point, making their confidence interval, and the example 2 on the birth rates page is one more example that is there for you. And then this is the end part of the without a standard deviation. We can go back and find the X bar by adding the lower confidence level and the upper confidence level together, dividing by 2. That's just the average. That's the same thing that was on your proportion slide. Okay, nothing new here. And we can find our margin of error by subtracting the two limits and dividing by 2. That's the same slide you had before. And then they're finding the sample size is a little bit different equation, but it will give us the minimum sample size that we need in order to be able to estimate the population mean. Okay, and there they give you one with checking it out there, finding out the IQ scores. This one was from your textbook, I'm pretty sure. And you're just finding the minimum sample size. Now, if you actually know, see, they're telling you they want a error that is 3. Okay, so they only want you to go up and down 3. And they want a confidence level of 95%. So they're telling you that, and then you're plugging this into the equation, and you're getting out 97 is the minimum number of students that you could have to get the estimate for the mean. Okay, so they're finishing that one up. And then estimating a population mean when the sigma is known. So now we're starting a whole new thing here. So remember, this is not a very normal situation. This is kind of an out-of-the-box situation because usually you cannot know the population standard deviation when you do not know the population mean. However, you're going to see that there are times that we have a large enough sample that we can say that our standard deviation of the sample is the same thing as the standard deviation of the whole population. So that's what we're coming to next, and then we're going to have a couple slides that just help us to know when to use the t-distribution and when to use the z-distribution, and then we're done.